We will now take a look at section 7.4, which is entitled Operational Properties 2, and we're going to begin by looking at derivatives of a transform. Let's suppose we have the Laplace transform of some function little f of t, which we call capital F of s. We know that this Laplace transform is a function of s, it's a single variable, and therefore if we wanted to, we could calculate its derivative. Let's calculate the derivative with respect to s of the Laplace transform, which is f of s. This is equal to, by definition, the derivative with respect to s of the integral from 0 to infinity of e to the negative st times f of t dt. Remember, the integration is not done with respect to s, it's done with respect to t, so we can move the differentiation onto the inside. Now, the function that's on the inside, when we look at this thing, we talked about this in terms of kernels and whatnot, but the inside function, the integrand here, is a function of both s and t. So when we pass the derivative to the inside, we want to denote that it's actually a partial derivative. It's going to be the partial derivative of that expression with respect to s of e to the negative st f of t dt. With respect to s, f of t is constant, so you can pull that outside of the derivative. This is going to be f of t times the partial derivative with respect to s of e to the negative st dt. And with respect to s, that derivative is going to be the following. We have f of t, the derivative of e to the negative st is also e to the negative st, and then from the chain rule, we need to multiply by the derivative of the inside function with respect to s, which is going to give us negative t dt. And we can kind of rewrite this if we kind of take a look at exactly what's happening here. I can pull the negative sign out. This is the integral from 0 to infinity. We have an e to the negative st, and then it's times t f of t dt, and this would be the Laplace transform of the function t times f of t. So what we have here is the negative of the Laplace transform of t f of t. Okay. So to summarize, what have we just shown? We showed that the derivative with respect to s of f of s is equal to the negative of the Laplace transform of t times f of t. Okay. Let's use this result to look at the following. This result will actually help us to find the Laplace transform of t squared times f of t. And we can do so as follows. To find the Laplace transform of t squared times f of t, let's write this as the Laplace transform of t times, and I'm going to put it in parentheses, t times f of t. Okay. It's essentially the same thing, but in terms of the form, look at what we have here. Okay. This Laplace transform we see from below, the Laplace transform of t times a function f of t is the negative of the derivative of the Laplace transform of s. So one of the things that we can kind of say immediately about this is that this would be equal to the negative, again, just kind of, if you take this formula, you could rewrite it just simply kind of moving the negative to the other side. The Laplace transform of t times a function, f of t, whatever you want to call it, is the negative of the derivative with respect to s of the Laplace transform function f of s. So this thing here, this entire expression, is like playing the role of f of t down here. So when you have t times f of t, it's the negative of the derivative of the Laplace transform of that inside function. So this is going to be the negative of the derivative of the Laplace transform of what I have in this parenthesis, t f of t. But we can play the same game again then, because, again, this fits that format where it's t, the Laplace transform of t times some function of t. So this is going to be, yet again, equal to the negative of the derivative of the Laplace transform of whatever the inverse, whatever the Laplace transform of this function f of t is. And if we look at what we end up getting, first of all, a negative times a negative is a positive. This is the second derivative with respect to s, and L of ft, that's what we simply call f of s. Okay. So start to notice a pattern here. When we have the Laplace transform of t times f of t, we get the negative of the derivative of f of s. When we take the Laplace transform of t squared f of t, we get the positive of the second derivative of f of s. And you can continue to use this property repeatedly, and what we get is the following result. So from this, we get what's referred to in the textbook as Theorem 7.41, which is about derivatives of transforms. We have the following, that the Laplace transform of t to the n times f of t is going to be equal to negative 1 to the n. There's going to be an alternating sign, as we kind of saw a moment ago, times the nth derivative with respect to s of the Laplace transform of f of t. Okay. So we have a nice result that tells us some of the operational properties that happens when we take nth derivatives of the Laplace transform. It also coincidentally gives us a way and a manner in which to find the Laplace transform of t to the n times some function f of t, which is going to be very, very useful to us kind of moving forward. Let's take a look at an example of one of these. In example 1, let's suppose that we're asked to evaluate the Laplace transform of t times the sine of kt. Okay. So to kind of give you a sense of exactly just how powerful these, these theorems are, try to do this with just the definition. Okay, it's a good challenge. Most of you, I'm sure, can do this. It's going to take a little bit of time, but it would require the use of integration by parts. You have to be very, very careful with your signs and whatnot. And you could probably find this Laplace transform simply by using the definition. However, let's be clever about it, and let's use our previous theorem. So this is t times the sine of kt. So the sine of kt is playing the role of like our function f of t. And from what we just said a moment ago, we know that the Laplace transform of t times f of t, this is equal to, it's going to be negative 1 to the first, which is simply going to be a negative 1, times the first derivative with respect to s of the Laplace transform of t, which we call capital F of s. Therefore, this is going to be equal to the negative of the derivative with respect to s of the Laplace transform of the sine of kt. That's something that we know from before. The Laplace transform of kt is going to be equal to k divided by s squared plus k squared. And now all we need to do is calculate that derivative. Okay. Again, I'll show it in more detail than what I probably would normally otherwise. But you can use quotient rule or a quick rewrite. You can use the chain rule. The negative sign is going to come down. Leave the k alone. It's a constant. We have s squared plus k squared now to the negative second power. And then from the quotient rule, from the chain rule, times the derivative of the inside with respect to s would give us 2s. So this is going to be a negative 2ks divided by s squared plus k squared squared. So don't forget, this negative sign was already outside, and now this derivative is coming in with its own negative sign. Negative 2ks divided by s squared plus k squared squared. And so for our final answer, we're going to get a positive 2ks divided by s squared plus k squared squared. And that is much, much simpler than having to do the formal definition for the Laplace transform of this function t times the sine of kt. So again, the benefit to this new theorem that we have is, in addition to telling us what happens with derivatives, it also gives us a convenient way to find the Laplace transform of some power of t times some function whose Laplace transform we know ahead of time. A couple other comments. We can also then use this to find the transform. If we want to, the Laplace transform of, let's say, some power of t times an exponential function. Remember, typically when you're trying to find the Laplace transform of e to the at, that kind of involves our good old school shift operator. So one of the ways that we can kind of handle this, right? Let's look at a concrete example. If you wanted to find, let's say, the Laplace transform of t e to the 3t. This can be done using theorem 7.31 from previous stuff, that this is simply going to be the Laplace transform of t, but with the shift s going to s minus 3. We know that the Laplace transform of t is 1 over s squared, and then we simply need to translate the variable s to s minus 3. So it's 1 divided by s minus 3 squared. So, be on the lookout. Just kind of recall that, when our function f of t is a special function, in particular if it's an exponential, that those are typically done using shift operators. You don't necessarily have to use the new theorem. But if we do it another way, let's kind of see how it would look. What if we were to do the same result, but using our brand new theorem? So let's find the same Laplace transform of t e to the 3t, but using our brand new theorem. According to what we just said a moment ago, this is t times e to the 3t is playing like the role of f of t. So this is going to be equal to the negative of the first derivative with respect to s of the Laplace transform of e to the 3t. We know that that's going to be equal to the negative of the derivative with respect to s. The Laplace transform of e to the 3t, that is 1 divided by s minus 3. To find that derivative, again, it's going to be helpful to rewrite it. Think of this as s minus 3 to the negative first, or you can do quotient rule. But this is going to be the negative of s minus 3 to the negative second, and then from the chain rule, we just simply get 1. So this is negative 1 over s minus 3 squared. So we get the negative of negative s minus 3 squared, which gives us the same result that we got above, but being done a slightly different fashion. Okay. So again, there's more than one way oftentimes to kind of use these. It's best to be really well versed in all of these Laplace transform properties so that you can apply them in many different ways. Of the two, not really one makes a big difference in terms of ease of use, but it's always good to be able to recognize when you might be able to apply a theorem in this context. Let's take a look at an example back to solving ODEs. Let's solve the differential equation x double prime plus 16x is equal to the cosine of 4t. And let's suppose that we have the initial conditions that x of 0 is equal to 0 and that x prime of 0 is equal to 1. We're going to start off by taking the Laplace transform of both sides. This would be the Laplace transform of x double prime plus 16 times the Laplace transform of x, and this is going to be equal to the Laplace transform of the cosine of 4t. Again, here notice that it's the function of x, it's x of t. So instead of calling it like y of s, this is going to be x of s. So the Laplace transform of x double prime, that should be equal to s squared times y of s minus s times y of z, excuse me, I just said it and I wrote it. So it's s squared times x of s minus s times x of 0 minus x prime of 0 plus we have 16 times this is going to be x of s, and now this is equal to the Laplace transform of the cosine of 4t. Okay. The Laplace transform of the cosine of 4t we know is going to be equal to s divided by s squared plus 4 squared, which is going to be 16. Let's now try to get rid of these constants and get all of our x of s terms to one side. X of 0, we know it's equal to 0. So this term will be gone. We know that x prime of 0 is equal to 1. So this is minus 1 plus 16 x of s. This is equal to s divided by s squared plus 16. I'm going to do two steps in one. Let's move this 1 to the other side. So we're going to add 1 to both sides. And then I'm going to factor out the x of s from the remaining terms. That's going to leave us with s squared plus 16 times x of s is equal to s divided by s squared plus 16 plus 1. And now finally we can get the x of s by itself. We're simply going to go ahead and divide every single term in the equation by s squared plus 16. These will cancel, so we get that x of s is equal to s divided by s squared plus 16 squared plus 1 divided by s squared plus 16. And now for our final answer, we just need to apply the inverse Laplace transform. So our ultimate solution, x of t, is found by doing the inverse Laplace transform of x of s. This is going to be equal to, again from linearity, it's going to be the inverse Laplace transform of s divided by s squared plus 16 squared plus the inverse Laplace transform of 1 divided by s squared plus 16. Okay. If we try to match this up with some of our known inverse Laplace rules, notice how we have a 16 here. This would be 4 squared. So we would like to have a 4 in the numerator. We can multiply the top by 4 if we simply multiply out in front by a 1/4. Okay. Now for this one here, notice that in the denominator, it's s squared plus 16 squared. And if you kind of look back at what we saw a little bit ago, we actually kind of worked this out in example 1. Okay. In example 1, that we just did a little bit ago, we found that the Laplace transform of t times the sine of kt was equal to 2ks divided by, oops, my apologies, come back, s squared plus k squared squared. And then therefore if I apply the inverse Laplace transform to both sides, what we should find is the inverse Laplace transform of 2ks divided by s squared plus k squared squared is equal to t times the sine of kt. But we need to get the coefficients to kind of match up here. So if you look in the numerator, we already have an s. Here, the thing that's playing the role of k, it would need to be the number that's being squared here. So k is equal to 4, but we need a 2ks in that numerator, which means we need a 2 times 4, which is going to be 8, which we can plug in as long as we put a 1 over 8 on the outside. And now this fits perfectly. This is going to be t times the sine of 4t. So for our final answer, we get 1/8 times t, the sine of 4t, and then this is going to be plus, we have 1/4, and then of course the inverse Laplace transform of this thing is simply going to be the sine of 4t. And that gives us the solution to our ODE.